Well, it should seem pretty obvious that something that's dark colored should heat up more than something that's light colored. If you've ever gone out on a hot day with a black shirt on, you can tell that the black shirt surface is much warmer than the white one. But this gets a little confusing if you've heard of Kirchhoff's law of thermal radiation. This states that for an arbitrary body emitting and absorbing thermal radiation that's in thermodynamic equilibrium, the emissivity is equal to the absorptivity. This is often said like this: a good absorber is also a good emitter. So that means that black things are good at absorbing radiation, but they're also really good at emitting it as well. This is because black is a good absorber of radiation, whereas white is a good reflector. But if we turn off the heat source, we can see that the black one will actually get cooler quicker. This is because it's emitting its radiation better than the white or gray one, so it cools quicker. So black things absorb radiation well, but they also emit it really well. And white things reflect it really well, but they also don't emit it very much. So will there actually be a big difference between wearing very dark clothing and just regular clothes? Well, let's see. Well, I found a study in 1980 that asked a similar question. The researchers wondered why the current inhabitants of Sinai, which is a very hot desert area, wear black robes instead of white. It seems that people would have caught on by now that white will keep them cooler. So they did an experiment. They took a person out to the desert and put them in a traditional robe. They measured the heat flow and temperatures all over the body. And they did this with their traditional black robes and also the white robes. And what they found was pretty interesting. They found that the amount of heat gained in the black robe was the same as the white. So it literally didn't matter what color the robe was. So what's going on here? Well, they did find that the surface temperature of the black robe was higher than the white one. But they found that the additional heat of the black one was lost through convection with the air before it reached their skin. So the skin always stayed the same temperature regardless of the color of the robe.
Today I'm going to be showing you the effect of intense heat on white and black clothes. So we have white socks and white shirts and black socks and black shirts. So we're going to actually see how a magnifying glass, this is a smaller one, we're going to use two magnifying glasses, a large one and a small one, to see the effect of intense heat on these clothes, the different absorption and emission, which one might burn first or which one takes longer to heat up.
Alright guys, so it's not that the white paper burns differently in the sun or that something is wrong with the sun. It's just more about absorption and reflection. So it's all about also I'm not faking the how I focus the light with the lens. So I use this one on the papers. If I use this big one, it's clearly gonna burn right through it. So it's just how long you leave the light on the white paper, because the white paper reflects more of the light. But if you shine it on the black paper, the focus will seem more intense because it reflects less and absorbs more. So even though I'm holding it at the same distance, it looks like it's focused more, while on the white paper it looks like it's not focused. So I'm gonna be putting the lens on a few items today, so including this basketball. So I'm gonna get this one pumped up. So there you go. Then also I'm going to test it on this black socks, this white shirt, this black sweater and this extremely long white socks. So I'm also gonna try and burn through the skateboard. And again, we're gonna pop this basketball. And just for good measures, I'm going to test it on the white paper and the white napkin. So immediately as the light touches the dark color clothes, it starts burning. So it immediately burns. You can literally track a line across the clothes. But when it goes to the white, it doesn't burn immediately. So if you held it for a longer time there, it might burn it, but it will take like exponentially longer. But as you can see, as it goes into the black, immediately starts to smoke, starts to burn it. Back to the white, nothing. As you go across to the black, it's immediately burning. It's literally catching on fire. That's how quickly the black absorbs all the heat while the white reflects almost all of the light. So yeah, that's what's happening right there. When you go over to the napkin, it's the same thing. Absorbs all the light. The black socks immediately starts to burn. So the focus is the same on both. It's just that the white reflects so much of the light that when you look at it on the camera, it looks like it's not focused. But on the black, most of the light is absorbed, so you can see the focal point. So yeah, that's how it works. If we go over to the much larger specs Fresnel lens, so we have a cinder block and granite stand. When you put the shirts on this, then this has like way more intensity. It concentrates a lot more light. So this one will definitely burn through the white shirt. Like the white shirt cannot resist this one. So if you take the white shirt here and you add it here, we'll see how quickly it gets burned through. So we're gonna test the white shirt. Let's get the sun to go through this one, and we'll see how it goes. This is definitely a monster. This one, it can go up to probably over 600 degrees, 800 degrees. It immediately goes over 100 degrees for sure, though. Over 300 degrees as well. So you'll see how once you get it positioned properly, you'll see how quickly it will go through the white shirt or catch it on fire.
will, it will go through it.
Go back that way.
So,
Go back that way. Okay, go back that way still.
so it's taking its time. The white is the white is very resistant to absorbing the heat. So yeah, there it is smoking. It's gonna burn right through it. But this one has way more intense heat. Yeah, this one is not plain. This one has so much heat. It's immediately burning the stick as well. So it's burning through the stick and burning through the clothes or the white shirt. Oh, the video is not sped up or anything. This is the real speed, real occurrence. And you see the white shirt takes a little while to get um, heated. Even though this is very intense heat, like this heat can melt rock, it can burn through a can of Red Bull, and there it is. It's burning through the white shirt. But this heat is reflecting so much light, you can't even see it properly. Like it's burning through. Now we're gonna test it with the black shirt. And you'll see how quickly the black shirt will start to burn. Once it's hit the black shirt, it's like it's an immediate effect. That's how hot. That's how hot this one is. So just positioning the camera. Let's see how it will go with this black shirt. There you go. And immediately start smoking. It didn't even take 2 seconds. It's immediately burning. And there you go. It's producing a lot of smoke. And actually, this black shirt is actually designed to be somewhat heat resistant and somewhat sweat resistant, but once the color is black, it's gonna absorb a lot of heat. So yeah, it's both the black and the white shirt got burnt right through, and that's how intense the light is. So now this is the effect that it has on a skateboard. Skateboard is blue. It's a board, so it's not metal. So the heat will get to it pretty quickly. As you see, it immediately starts to burn. So I didn't. It's not like a plastic skateboard, so it's or something plastic. So that would probably burn a lot faster. This is just regular wood,
Basketball
so
more or
it's
less.
gonna burn at that speed. Um, so yeah, that's what it's doing to the skateboard. So you see, it's actually very hot. And yeah, the glare from this setup can be very bright, so you have to wear like protective eyewear. This is This is now the effect on the basketball and immediately starts to burn. This basketball is somewhat heat resistant, even though it's all rubber and just air, but it survived pretty long under this hundreds of degrees of heat. You can see it's being distorted where the focal point is. Like you see that bulge that forms. So it ends up forming a protective coat. So you have to keep the heat on it a bit longer before it pops. I thought the pop would have been somewhat explosive, but it just it just aired out. Like if you pop if you poked it with a needle or something, it'll pop explosive like a balloon. That's the damage. So all the heat was concentrated to one area, and that's the area that really got burnt and small. It didn't really spread. I guess rubber is somewhat insulating. It's like an insulating type material, so the heat on it would not necessarily spread, and so it didn't catch fire. It didn't burn all the way through. It just popped, and there's no air in it, but it was still it still looked like a fully inflated basketball.